InterFET, the world's largest supplier of JFETs. In this video, we will explore the design of a planar JFET. As a starting point, let's look at a slab of N-type semiconductor material and attach wires to opposite ends. An applied voltage will cause a current flow from one end of the material to the other. This chunk of material will act like a resistor. As the voltage is increased, the current will increase. By changing the amount of N-type dopant, we can control the resistance at the time of manufacture. Such a structure is not useful as a circuit element because a standard off-the-shelf resistor is much easier to make and therefore cheaper. If we put a layer of P-type semiconductor on the top and bottom of the central piece of N-type material and add a third wire to these new layers, we find that we can now vary the conduction through the central N-type material. This happens when a negative voltage on the P-type material causes the electrons in the central region to move away and create a depletion region. In this depletion region, there are few charge-carrying electrons, so the resistance appears higher when there is a negative voltage on the outer material. It is the electric field that causes a shortage of charge carriers. For this reason, we call this device a field effect transistor, or FET. Because the proximity of an N-type material and a P-type material form a junction, we call this a junction field effect transistor, or JFET. In this case, the channel is made of N-type material, so it is an N-channel JFET. The three terminals of a JFET are called the gate, drain, and source. The drain and source are at either end of the channel. In a symmetrical JFET, the drain and source are truly interchangeable. The gate is the control terminal that applies a field to the channel. We will call this wire the gate because by opening the gate, we can get more current through the device. The source is where electrons enter the device, and the drain is where electrons are drained away from the device. While this simple model explains how a JFET works, it is difficult to manufacture. Planar JFETs are manufactured in a different way. To begin with, we will use a pre-manufactured wafer that has a P-type substrate with an N-type epitaxial layer grown onto the substrate. Because this layer is slowly deposited on the substrate, the molecules of the P-type substrate align well with the N-type epilayer. If we cut the wafer in half, it will look like this. The N-type layer is thinner than the P-type substrate. We can now use the standard semiconductor process of masking and etching to produce a JFET in the N-type epi layer. A rectangular area of the N-type epi is cordoned off as a well to hold the JFET. The well is created by converting the N-type epi layer to P-type material in the shape of a rectangle. To do this, the surface of the epi is covered by a mask that protects the area we do not want to convert. Then, using either ion implementation or chemical deposition, the enclosing well is created by converting the N-type epi to P-type. The conversion goes all the way down through the N-type epi layer and connects with the P-type substrate. The concentration of dopant in the walls of the well is high enough that it is essentially the same as the P-type substrate below, and both the well and substrate can be considered as an electrical conductor. We now have an area that is isolated to form the JFET. All of the structures we create inside the well and the well itself will make the JFET. Thousands of wells are created on the wafer at the same time. Let's focus on just one JFET. This JFET will consist of several cells that are side by side. To create them, we will further partition the well by forming a structure that will become the gate. In our N-channel JFET, the gate will also consist of P-type material. This gate structure will be electrically connected to the walls of the well, but will not connect with the substrate on the bottom. We need to leave some space between the bottom of the gate and the top of the substrate for current to flow in the N-type channel. So instead of a straight channel like the simple model, the planar JFET will have a U-shaped channel. The current will flow from the drain connection at the top, down through the channel under the gate, and back up to the source terminal on the far side of the gate. By shaping the channel in this manner, we can now add a layer of metal fingers that allow us to connect the cells to make a single JFET. The metal fingers will interlace when viewed from the top. The fingers will run to a small pad that can be used to bond to the leads of the JFET package. This is still a simplified model. Actual semiconductor processes are more involved than what has been presented here. There are more steps in the manufacturing process because the masking procedure uses an oxide layer that is removed and added in successive steps as the microstructures are created. Also, after ion implementation, the wafer must be annealed to allow the atoms to settle back into the crystal structure. Each heating process causes atoms at all the boundaries to diffuse slightly. In addition, the diffusion and ion implementation processes are easily affected by temperature and the chaotic movement of atoms. Also, because the extreme purity of the materials cannot be guaranteed, it is difficult to make JFETs with precise parameters. As a result, there will be significant variation in the performance of the thousands of JFETs manufactured on a single wafer. Because of these process difficulties, each JFET will have to be electrically tested to determine its performance. Additionally, many manufacturers provide custom screening for parts that must meet tighter specifications. If you enjoyed this video, give it a thumbs up and subscribe for more expert insights into JFETs, analog design, and low-power electronics. Hit the bell icon so you never miss an update from InterFET. Got questions or ideas for future videos? Drop them in the comments. We'd love to hear from you. Interested in using JFETs in your next project? Reach out to us directly through our website or the link in the description to speak with our team of experts. Stay connected, stay curious, and keep innovating with InterFET.